Hello everyone, welcome to the Introduction to Mechanical and Industrial Engineering course, MEC 130. This is the second video in this subject, which is thermal and energy systems. And over the previous video, we define what does it mean: force, work, energy, power, the difference between these different physical quantities. Also, we define different forms and types of energy. We discussed what does it mean, the potential energy, whatever it is, gravitational potential energy or elastic potential energy. Also, we discussed the kinetic energy, and then we discussed that the conservation of energy principle. We said that the energy that is required to move an object, it is conserved as at any position, at any instant of time, so it should be all the time conserved or preserved. And this is what we discussed over the previous video. Even we solved this example. So over today's video, we are going to discuss another form of the energy, which is the heat. Heat, it is one of the forms of the energy. So heat, it is a form of energy that makes atoms of the material move to increase the material temperature. So this is like the conductivity of heat. Like if you have a heat source that is or amount of heat that is directed to a certain material, this material, it will be heated up. The heating within the material, it will result in a change in the temperature, mostly by increasing the temperature of the material. So the increase of the material, this requires a certain amount of heat that we should give and deliver to this material. But to absorb temperature, to absorbing the heat, we can absorb a heat from the material. The absorption of the heat is going to result in a decrease in the temperature. So the change in the temperature, whatever with an increase or decrease, this requires either delivering or absorbing energy from the material. This energy, it is heat. This type of the energy, or this form of energy that is needed to change the temperature, is known as the heat. So the heat, in a way, it is an energy, and that's why the unit of the heat, it is in joules, if we're going to talk about the metric system or the international unit system. So again, heat, it is a form of the energy that is needed to change the temperature of a material. And mostly it's going to be used with the tendency of increasing the temperature of the material as long as this heat is delivered, is sent to this material. When an amount of heat is delivered to a material, the material temperature is going to increase according to this expression. So Q, this is the amount of heat that it will be sent to the material, equal the M, which stands for the mass of this solid object, which it should be in kilograms as long as we are working with the international unit system, or slug in case that we are working with the US unit system. And see, this is the object's specific heat. This heat, it is a material property that depends on the material type. This specific heat, it is, you could understand it based on the ability of the material to absorb and make use of this heat to increase its temperature. Like for example, you could deliver a certain amount of heat to a material, and for some reason this material is insulating material that won't gonna feel with this, or won't gonna make use of this heat, and instead it's going to dissipate and push back this amount of heat or this energy. So the ability of the material to absorb the heat that already delivered to it, this is measured by a factor or a measure known as the specific heat, as a material property of the material, which it could be measured, the unit, it is joules per grams, kilograms times degrees Celsius, or in pound-foot per slug degree Fahrenheit, in case that we are working with the US unit system or the SI unit system. Make sense? So this will result in a change in the temperature T negative T0. T0, this is the original temperature, like this piece of metal. It was already at a certain temperature, then we are going to expose this metal into a certain amount of heat, so it's going to be heated up, and the change in the temperature, this is going to make this T, new T, this is the new temperature after delivering the heat, is going to be bigger than the T0. But in case that this T is lower than the T0, this entire right-hand side is going to be negative, indicating a negative heat. A negative heat, it means that we are absorbing heat. We are taking heat from this material. Like if you have a hot piece and you're going to put it over a cold ice, so the cold ice is going to absorb, it's going to cool it down. So in that case, you are going to decrease the temperature. So in case that the temperature increases, as a rise in the temperature. So T negative T0, this is the temperature rise or temperature increase due to the addition of the heat. And in case that it is a decrease in the temperature, so it should be negative, and in that case the Q is going to be negative. Make sense? So this is simply what does it mean, heat. Again, it is another form of the energy that is mainly used to transfer the heat through the material with the aim of increasing or at least changing the temperature of a material part. This requires a certain amount of energy, which is known as the heat. Make sense? So how the question is, then another important subject which is related to the heat energy and thermal system is the heat transfer. Heat transfer is the process of the transfer of heat from high temperature reservoir or source to low temperature source. And in case, for example, if you do have a material, this material you are sending heat. How can we send the heat? To send the heat, you have to build a system. This system should have two sides. One side it should be with a high temperature source, and the other side is going to be with low temperature reservoir or source. So the heat will be delivered and it's going to flow in a certain direction from the high temperature source to the low temperature source. So with this way, we can control the transfer and the direction of transferring the heat from one source to another source or from one point to another point. So to deliver the heat in a certain direction, we have to set up a system. This system is going to depend on the concept of the heat transfer. What does it mean, heat transfer? It means that this is the method or the approach by which, or the process by which the heat it will be delivered in a certain direction from the high temperature source to the low temperature source. And to transfer the heat, there are lots of mechanisms that could be used. The three sources of heat transfer are the conduction, convection, and radiation. So what is the heat transfer by conduction? Heat transfer by conduction, it is a mechanism. So it is one of the mechanisms of the heat transfer, one of the methods of transferring heat from one source to another source, from the high temperature source to the low temperature source of heat transfer between two solid objects or bodies at two different temperatures. Heat is going to transfer from the solid with a high temperature to the one with a low temperature. So the condition is that the conduction requires a solid medium to allow for the heat transfer in a certain direction. Like you should have one over this side, for example, we do have a high temperature source. This is a high temperature source, and we're gonna have another temperature source over the other side. But here the temperature is low, but the temperature here is high. So the heat is going to transfer, and somehow these two sources are connected together by a solid object. This is the condition for the heat transfer by conduction. This requires a medium, something to transfer, a bridge to allow for the transfer of the heat from the high source temperature to the low source temperature. So this, in case that this bridge or this medium is a solid, so the type or the mechanism by which the heat is going to transfer, it will be conduction. So the heat conduction, this requires a bridge. This requires a solid medium to allow for the transfer or the heat transfer between two solid objects or bodies or two different sources of temperature, different temperature. The heat will be transferred through the solid with a high temperature from the high solid with a high temperature to the one with a low temperature. So this is the heat transfer by conduction. Again, it requires a solid medium to allow for the heat transfer. We start from the high side. Assume that this side is at a temperature that is bigger than the temperature of the other side. So definitely there should be amount of heat that is going to feed and transfer in this direction, and this is going to be the direction of the delivery and sending the heat from the high source to the low source. Make sense? The other mechanism is convection. Convection, it is the mechanism of heat transfer between a solid surface and a fluid. This requires fluid. Convection requires that there should be a fluid, and this fluid is going to be the medium that is going to be used for the transfer of the heat. And mostly it's going to be the transfer of the heat between a solid and the fluid. As we discussed in the fluid engineering, we said that in many of the cases, the use of a fluid requires using the fluid in connection or conduction with a solid object. For example, if you do have a liquid, to collect it, it should be put it in a container. It should be put it in a cup. It should be put it in a solid object. So it means that all the time the fluid will be in a contact with the solid object. So if you are going to heat the solid object, this heat will be delivered to the fluid through the solid object by conduction, and then it will be processed through, or go through, the heat will go through the fluid by convection. So convection, this is the heat transfer that requires a medium, and this medium, it should be fluid, whatever it is, air, as gas, or as fluid, liquid. So for example, if you do have, let's say like a pool of water, and for some reason you're just gonna put some hot source here, like you're gonna put a probe that generates heat within this water. So this amount of water, or the region around this probe, will be around the source of heat, it will be very hot. The amount of water around it, it will be very hot, but then after a while the heat will start to propagate, and the other parts of the liquid will be heated. And this is the same concept like the boiler, how we boil, for example. So we start with a source of heat that is located somewhere, and then the heat will start to propagate and expand over the entire liquid. So the transfer of the heat from the source, from this source, which is gonna be solid object, solid hot object, and is going to transfer to the liquid with the aim of heating the liquid. So this requires convection. So this is another mechanism of the heat transfer, which depends at another mechanism is known as the convection. The third mechanism is radiation. Radiation is a mechanism of the heat transfer between two objects of different temperatures and separated by a distance. It means that they shouldn't be in direct contact. This is the heat transfer by radiation. Radiation doesn't require a specific medium to allow for the heat transfer. It means that the heat could transfer through solid objects, through fluids. Also, it could transfer in vacuum. Vacuum, it means that there is no specific bridge between the two objects, even if there is no bridge between one source. Like assume that you have two sources, one source of high temperature, this is temperature source, and there is another temperature source, but they are not connected with neither solid nor liquid. If there is a liquid, we can transfer the heat from the high temperature source to the low temperature source through the liquid. So the liquid is going to work like a bridge to allow for the heat transfer. We also can transfer from the high temperature source to the low temperature source through solid bridge. We can set up a solid material here, and this is going to be the conduction. Also, we can even transfer, the heat could transfer from the high source to the low source by radiation with no need to a solid bridge or a fluid bridge. It means it could be transferred in vacuum, and in that case we're going to have the radiation as another mechanism of the heat transfer. It means that it is not necessary that you do have a specific medium to allow for the heat transfer, and instead it could transfer in vacuum. So radiation is a mechanism of heat transfer between two bodies or objects of different temperatures and separated by a distance. The radiation heat transfer requires no medium. There is no need for a specific bridge, as I said, or medium to allow for the heat transfer. The radiation heat transfer occurs due to the electromagnetic waves. This requires electromagnetic wave that exists in the atmosphere, and thanks to these waves, this electromagnetic wave is gonna work like the medium that is going to be used to allow for the transfer of the heat by radiation from the high source to the low source. This is the same concept of the radiation heat that we receive that is transferred to the earth by the sun. The sun delivers heat. The earth is heated by the sun, but there is no specific medium. In space, it is totally vacuum. There is no specific medium or air or fluid or solid that is going to use for the transfer of the sun heat to the earth. But the earth, it is heated by the sun. How? Through this electromagnetic waves by a mechanism known as the radiation. So these are the three mechanisms that used to describe the way of the transfer of heat from one high temperature source to a low temperature source. Make sense? Alright, so this figure gives a very good summary of the different mechanisms that we mentioned here for the heat transfer: conduction, convection, and radiation. Like, for example, this is the process of boiling water. So as you can see, we have the three mechanisms are exist in this example. Like, for example, the first thing is the conduction. Conduction, as we mentioned, this requires solid medium to allow for the heat transfer from the high temperature source to the low temperature source. So for example, your bare hand, it is at low temperature reservoir. It is at low temperature, it is at the room temperature in the beginning, and the water itself, this is the hot source. This is the hot part. So this is the hot temperature source, and the heat is going to be transferred from the hot side to the cold side through a solid medium. So as you can see, the handle or the hand of this container will be heated up because the heat will be start to transfer through the solid hand. And thanks to this hand, you're gonna feel with some heat in your bare hand, right? So this metal part or this solid part, it was used to bridge the gap or to bridge the heat transfer from the high source to your hand, which is at low temperature level. In that case, you're gonna feel with some heating up in your hand because of the solid part. So this is a heat transfer through the solid by conduction. The other mechanism is convection. Convection, it means that because as you can see, the heat of source here is going to heat the solid part or the solid container first. Then the heat, it will be transferred through the solid container to the fluid to heat the fluid. So the heat will be transferred through the fluid. Through this fluid, it means that the fluid is going to be the medium that is going to be used. The water is going to be the medium that is going to be used for the heat transfer. And this is another mechanism known as the convection. So the convection requires a fluid medium for the heat transfer. But in the meanwhile, if there is someone else, some other guy who is just putting his hand next to the fire, he's gonna feel with some warm and heating in his hand, bare hands, because of the fire. While there is no specific medium there, air, it could be considered as a medium, but it is not the specific medium. It is not strong enough to support the heat transfer, but instead, you're gonna feel with some warm and heating in your bare hand as you come close to the fire. The reason is because of the radiation, which is the third mechanism. Radiation, as we said, this requires electromagnetic wave that is found in the environment, and this is what is used to support the transfer of the heat from the high source from the fire to your hand. So these are the three different mechanisms of the heat transfer that we discussed, and this figure gives a summary of these mechanisms. So here we're just gonna focus on one of the important mechanisms for the heat transfer, which is the heat transfer by conduction. And we're just gonna study, I'm just gonna give you an idea. This is just an example about the thing that you should expect when you take the course of the heat transfer. There is one of the courses that you're gonna study, whatever your major is, mechanical engineering or industrial engineering, you're gonna study some courses related to the thermodynamics and the heat transfer. So what is the subject or the concern of the heat transfer course is to study these different mechanisms of the heat transfer and understand them for different applications. One of these mechanisms, for example, just to give you an overview how we can calculate the amount of heat that is going to be transferred by conduction through a solid object from a high source to a low source, this could be calculated using this expression. So this Q stands for the amount of heat, that this is the heat energy, that it will be delivered from the high source to the low source, equals chi A delta T divided by L times the T high negative T low. So T1, this is not 1, this is TL stands for 2, T low, the low temperature, T high, this is the high temperature, delta T, this is the time period for the heat transfer, and A stands for the cross-sectional area that is exposed to the heat. We are sending the heat through this solid object, and this is the cross-sectional area that is normal to the direction of the heat transfer through the solid object. So this is the cross-sectional area. L, this stands for the length of this solid part, and chi, this is the stands, or K, this stands for the thermal conductivity. What is the thermal conductivity? This is a material property that depends on the material type of this solid object. Depending on its material type, it gives it ability to allow for the heat transfer. So the thermal conductivity is a measure of the ability of this material to allow for the heat transfer through the solid material. Probably, for example, depending on this K, the heat could be delivered from this point and is going to keep on proceeding up to this point, but while the other parts of the solid object won't going to feel any change in the temperature because of the amount of heat. But in case for another value, in case that this K value is big enough, it means that this material, it can be heated up very quick as long as it has a high thermal conductivity. So it is a measure of how the material is going to be heated by heat transfer through the conduction or through the solid object. So from this expression, we could calculate lots of things. For example, if you do have a source of heat, like you are going to deliver a certain amount of heat over this cross section in this direction, going to the right direction, as already represented here. So the question is, what should be the changes in the temperature over the other side? So the other side, it should be at a certain temperature. Let's say that it is at a certain temperature like T low. So this is the temperature, the low temperature level, or this is the original temperature of the entire solid object. Then we are going to send the heat over this cross section. So the heat will start to expand, the temperature will start to increase through the different points of this bar till it will reach up to the other point. But this is going to take time. The heating process is going to take time, and this makes sense. For example, when you boil water over the stove, this is going to take time till it will be boiled. So it means that the heating process requires time. So that's why we do have in this expression the delta T. Delta T stands for the time needed to heat the material. So for example, if you're going to keep on sending this amount of heat through this section, through this cross section for a certain period of time, what should be the change over the temperature at that point, at the other point, at the other side? The temperature it was before we send the heat was T low. This temperature after we send the heat, definitely the temperature is going to increase to be T high. So what is the new temperature? What is the increase in the temperature? The increase in the temperature is going to be the difference between the T high negative the T low. At this surface, if we're going to keep on sending this heat through this cross section from that point to propagate and conduct through the other side for 1 minute or 2 minutes, 1 hour or 2 hours. So as we're going to keep it for a long time, we are expecting further changes in the temperature. So if we're going to keep on sending this heat for a certain period of time, what should be the change in the temperature over the other side? We can calculate it using this expression. So as I said, this expression depends on the material property that is represented in the thermal conductivity, and this table gives the different values of the thermal conductivities of different materials depending on the material type. We said that this is a material property. For example, the steel, it has a thermal conductivity of 26 if we are working with the US system, or 45 watt per meter times degrees Celsius. This is the unit for the thermal conductivity. Copper, it is more conductive than steel. Steel, it can conduct heat, but it is not more efficient in the heat conductivity like copper or aluminum. Aluminum, it has 200 thermal conductivity. Copper, it is more conductive than aluminum. It is 390 thermal conductivity, but the steel is 45 only. So these are still good conductors because they are metal. But if you're going to compare these to the glass or even to the wood, so their thermal conductivity is too low, especially the glass. Glass, it is ceramic material. And if you recall, when we were discussing the material types, we said that ceramics, they are good insulator for heat and electricity. Ceramics, like the glass, it is one of the ceramic material. It is a good heat insulator and it can support high temperature, and it is barely can be used for heating up. So boilers, most of the boilers and these things are mainly preferred to be made of aluminum, copper or steel, or the container that we are using for the food making are mainly depending on these steel, copper or aluminum. But glass also we can use it for heating, but it is not efficient for the heat transfer by conduction like the other metallic elements. Make sense? So this is an example here as a practice over this expression. So we already defined the Q as equal to the thermal conductivity times the cross-sectional area delta T, which is the time divided by the length of the object. This gives time the change in the temperature from the low temperature to the high temperature. So this is the heat transfer by conduction expression. So if you have a steel bar with a thermal conductivity that is given by 45 watt per meter degrees Celsius, as already we mentioned, the steel has 45 thermal conductivity, 0.6 length. So the thermal conductivity, which is chi or K, it is 45 watt per meter degrees Celsius, and you do have the length, it is 0.6 meter. So you just collect the data that is given here, and 0.02 meter diameter. So the diameter of this steel bar, it is 0.02 meter. Anything that has a diameter, it should be like having a cylindrical piece, like this object. It has a circular cross section. So if I ask you to calculate it, why we need the diameter? Because we're gonna use it for the calculation of the cross-sectional area. So simply, how we can calculate the cross-sectional area that found in this expression, the area is gonna be pi over 4, the diameter square, which is gonna be pi over 4, 0.0 square. Then you can simply do the calculations. You're gonna end up with the cross-sectional area. Make sense? Shift pi divided by the 4. This is gonna give us 3.14 times 10 to the power negative 4. Make sense? So this is for the cross-sectional area in meter square that we just calculated. Then carry on, we do have here is heated from one end. So we do have this steel bar with this specification, length and diameter, and the thermal conductivity that is made of steel, and it's going to be heated from one end, typically the same like this example here, that this is the heat source that we have. If the heat source delivers amount of 560 joules, so from the unit we could understand that this is energy. The energy, it is measured by a unit, and the thing in this expression that is counted as energy is only Q. So this is the amount of heat, and remember that the heat, it is one of the form of the energy. So that's why it is given by 560 joules at this source. So at this end we are delivering or sending this amount of heat, which is 560, and the heated end is at 300 degrees Celsius. Calculate the temperature of the other end after 300 seconds. Or in other words, we could say that this bar is already at a temperature which is 300 degrees Celsius. So this will be counted as a low temperature. It is 300 degrees Celsius. So the 300 degrees Celsius, this is the temperature of the entire bar, because he mentioned the heated end, it was at 300 degrees Celsius. So the heated end, because before that, before we delivered the heat, there was no heating already to this bar. This bar, it should be uniform at the same temperature level. So assume that it is already at the same temperature level. So the temperature at any point before we delivered the heat, at any point of this bar is already 300 degrees Celsius, as already mentioned. So we're gonna consider that this is the 300 degrees Celsius. And at any point, so if there is a specific point at the other end of the bar, which it should be at low temperature of 300 degrees Celsius, what it should be this temperature after a specific period of time? What will be the change in the temperature after a specific period of time? So it was required to calculate the temperature at the other end after 300 seconds. So delta T, this is the time, it is 300 seconds. So what should be the temperature change? So simply it is a very straightforward direct substitution into this expression to calculate this TH. So the unknown in that case, the unknown definitely is gonna be the high temperature, how much it is. So your objective is just to extract the given information, what is given, what is unknown, and then substitute into this expression. So we do have the Q equals the K, which is thermal conductivity, the cross-sectional area, the time change, or the time divided by the length, times the temperature high negative the temperature low. So this is going to give us equals. Your objective is just to substitute with the given data. So the Q was given by 560 equals the K, which is 45 times the cross-sectional area, which we just calculated by 3.14 times 10 to the power negative 4, times the delta t, which is the time, which is 300 seconds as already given, divided by the length, which is already given by 0.6. Make sure that the length or the dimensions in meter for the area and the length as 0.6, times the TH negative 300 degrees Celsius. So this is the T low is already given. So as you can see into this equation, we have only one unknown that can be solved for the high temperature. So if you solve, you're going to end up with the temperature at the other end of the bar after 300 seconds. If you're going to leave it for a long time, this temperature definitely is going to increase. So if we did the multiplication, we're going to end up with this value. So it will be 379.26. So this is going to be the new temperature at the other end. If we decided to calculate the change in the temperature, your objective then is just to subtract TH negative, the T low, you're going to end up with the change in the temperature because of this amount of heat that had been delivered in 300 seconds. Make sense? The second example is typically the same. Like the K was given, the thermal conductivity was given by 45 watt per meter degrees Celsius, and you're gonna have the length is still the same, 0.6 meter, and the diameter it is 0.02 meter, and from this we calculated the area by 3.14 times 10 to the power negative 4 meter square, right? And it's going to be heated with the same source of heat, so the Q is still the same, 560 joules, and the heated end is at 300. It means that we assume that the whole bar it is at this temperature level at 300 degrees Celsius, and calculator is required to calculate the time needed for the other end to reach. It should be like 400, for example, 400 degrees Celsius, like our 1000 degrees Celsius. Let's say that it is 1000 degrees Celsius. Why? Because the temperature, it should be bigger than the temperature over the other, because we are delivering heat. So if the heat source deliver, it means it sends, it gives. So it should be heated up, not absorbing. We are not absorbing heat from this heated bar, but instead we are delivering heat by 560. So we are expected an increase in the temperature over the other side of the bar to 1000 degrees Celsius, for example. So how long does this process takes for the other end to be heated? So it is very similar to the previous example, but the only difference is in this case, and instead of giving you the temperature, giving you the time, and it was required to calculate the temperature after heating at the other end. The temperature after heating, it was already given, which is the high temperature in that case is 1000 degrees Celsius as given. So what should be delta T? So the only unknown is going to be the delta T. So it's going to be the same still expression as K times the area delta T divided by the length of the bar times TH negative T low. And your objective now is just to calculate the delta T, which is the time. So do the substitution. We do have 560 equal the thermal conductivity, which is 45, times the cross-sectional area, which we just calculated 3.14 times 10 to the power negative 4, times delta T, we have no clue how much it is, divided by the L, which is 0.6, times the 1000 negative 300. Then if you're going to end up with one equation, only one unknown, which is the delta T, the time needed for heating, you're just going to calculate it, and it should be in seconds. It should be in seconds in that case. So this is going to give the time at 33.97, which is going to be like around 34 seconds. It means that for this heat, for the other end, to be heated at 1000 degrees Celsius, we need a time at 34 seconds. So this could be kind of confusing here, just to understand this concept. Here, there is something to understand, because, for example, in the previous example, we took 300 seconds to heat, to reach the temperature, to increase the temperature from 300 to 379 in 300 seconds. We just increased the temperature 79 degrees Celsius. But after 34 seconds, we are going to increase the temperature into 700 degree with a 700 degree into to 1000 degrees Celsius. So how come? For example, the 300, we increase the temperature just for 379, and the 34, we increase up to 1000. How come? How it works? So this is something related to understand it. This is something related to the heat rate, the heating rate, the rate by which we are delivering the heat. For example, for this bar, that at a temperature at 3 degrees Celsius, this is the current temperature of the bar. So in order to heat this bar, in order to heat the bar entirely in such a way that it's going to make the other end at 1000 degrees Celsius, we have to send the heat at a certain rate. The speed of sending the heat, it should be high, and we should deliver this heat very quick within a period of time only 34 seconds. So this is the time that is needed to deliver the heat in order to heat the entire bar. If you are going to heat the bar for a longer period of time, then this one, or the delivery of the heat is going to take longer time than this, we will not be able to heat the other end to the 1000 degrees Celsius. This is how we can understand it. So it is basically, there should be like Q divided by delta T. This Q by delta T, this is known as the heat rate. This heat rate, heat transfer rate, it should be very high rate. We have to send it very quick, so we would be able to heat the other end up to 1000 degrees Celsius. But if we are going to send the heat at a slow rate, and the delivery of the heat is going to take 300 seconds, it's going to take long time, we will not be able to heat the other end up to the 1000, and instead we can heat it up to the 379.26 degrees Celsius. Make sense? So this is how we can understand it. And again, there are lots of other things that you are going to cover when you study the heat transfer course. As I mentioned over this introduction to mechanical and industrial engineering course, the objective is just to give you an overview, a hint ahead of time before you study this heat transfer course. What are the things that you are expected in this course? Again, it is more relevant to the heat transfer and heat conduction and heat application of the different thermal systems. Make sense? So that's it for this video, and that's it for this part of the thermal and energy system. And yeah, so that's it for this video, and thank you so much for watching, and see you in the next one.